Good morning, geometry. Let's talk here. We're in our fifth section of chapter 5, and we're talking about a couple of relationships that we're going to get in triangles, typically similar triangles, but sometimes similar triangles are going to be formed. So the first one we want to talk about the angle bisector theorem. So if an angle is bisected, as you see exemplified over here, the angle bisector, this, cuts the opposite side, one away from the angle, proportional to the sides of the angle. Or some people like to say this side is cut proportional to the other two sides of the triangle. However you want to look at it, however you want to say it. So what's that mean? That means if I know I got an angle bisector, I can find some missing segments and by setting up some ratios. So I'm going to compare A to B, side of the angle, side of the angle. And it will be equal to, now look, again, going back to that theme of making the same comparison, I went with the bottom part. So I'm going to take the bottom part, compared it to the top part, so to the top part. You can do it that way. Some people are going to say that I want to compare top triangle to top part, okay? B to Y. Bottom triangle to bottom part. Notice AY, BX, AY, BX. You get the same cross products. Make the same comparison. That key theme keeps running through and through. Make the same comparison. So let's put this in play here for us. Let's look at this example. We got to find the missing side here, X. What do we know? We got an angle bisector. So that's telling me that I know this side is cut proportional to the ratio of these sides. So how do I want to compare them? That's up to you. I'm going to go top triangle, bottom triangle. When I say triangle, I mean full part, not a portion. So I'm going to go 18 over 14, and I'm going to compare it to top to bottom equals x over 6. Now, some of you will see things differently in what you're doing. It's completely up to you. Some of you will just run right away and say 14x is equal to 108. Some of you might look at it like this and say, oh, I can reduce these things. And that would give me 9 over 7 equals x over 6. 7x equals 54. Okay, either way you want to do it. Both ways are going to work. 7 goes into 54 7 times. 49 and 5/7. You're going to do this one up here. 14 goes in 7 times with 10 left over. and then I got to reduce one more time. So reducing here avoids me having to reduce there and using larger numbers. That's all. Okay, let's look at our next portion of this. Medians. Remember, what's a median do? A median connects one vertex of a triangle to the midpoint of the opposite side, so they're cutting opposite sides. So they're going to be cutting opposite sides in half. So now, as we work with this, the triangles are going to have to be similar right off the bat. So medians and similar triangles. Medians and similar triangles, we can set up that the ratio of sides will equal the ratio of any segment in the triangle. What has to happen though first? They got to be similar. Not similar, not working. Not similar, they're not working to it for us. So, I've got a couple things labeled here. A couple things we can do. I labeled limited, but some people will look at it this way. Side of the triangle, so I'm going left triangle to right triangle. Compare my medians the same way. The medians correspond to each other just as much as these sides correspond to each other. AB, LM. So this median, 8, from the left side, compared to the median there. Some people will reduce, some people won't. Now somebody will say, well, yeah, that one's half, that one's half. Okay, good. You saw the ratio in your head. Awesome. I'm setting this up because you might not always see that ratio right off the get-go. So ratio of sides will equal ratio of any segment. So that segment's in the triangle, so those sides, segments in the triangle. We'll look at this for a mid-segment. First off, what's a mid-segment do? It connects. Definition of a mid-segment. Midpoints of two sides of a triangle. That's our definition. Then, what do we know then? It will be two things we know. The mid-segment will be parallel to the third side, the one it doesn't touch. And we also know it will be half the distance of the third side. Similar to the mid-segment in a trapezoid. Not exact, but similar. How will I know when I have a mid-segment? I'll see these things. They're cut 1 to 1. 1 to 1. Cut 1 to 1. A couple more relationships that came up on some of the worksheets, but let's make sure we have them down. Oops. And it's going to look like this. So in similar triangles, first thing, if you can see it, it'd be awesome. There we go. First thing, the ratio of the sides, also known as your scale factor, will be equal to the ratio of the perimeters. I should put a plural on that. So I'll take a small triangle, Compared to large triangle, I go side to side, I can go perimeter, perimeter. Another relationship. If you take the ratio of the sides and square that fraction, it will be equal to the ratio of the areas of the figures. So square the ratio of the sides, it will equal the ratio of the areas. And thirdly, if you cube the ratio of the sides, notice volume is a cubic, it will equal the ratio of the volumes. So let's look at this in action here. So we're looking at this problem. And in this problem, it states that triangle ABC is similar to triangle XYZ. All right, so we're being told that. The perimeter of triangle ABC is 18 meters. Okay. The area of triangle XYZ is 50 square meters. Notice we don't have all the information. We're being given stuff. Find the other perimeter and find the other area. So we need to find the perimeter of this one. We need to find the area of this one. And that goes back to using these relationships. So let's see how we can do this. First off, let's figure out a scale factor. Some people are going to go ABC to XYZ. Some people are going to go reverse. That's your call. I'm just going to go left to right here. So I'm going to make my comparison triangle ABC to triangle XYZ. Meaning, again, XY is first, AB is first, segments there. I'm going to have an 8:3 scale factor, or ratio of sides. I'll call it scale, less words to write. I'm going to use this in the rest of my problems. All right, so let's go, what I want to find first? Perimeter. Okay, we know the perimeter of this one. So make the same comparison. So to find the perimeter, I'm going to go 8:3 ratio of sides equals, and I went triangle ABC, so I need that perimeter, 18 meters, compared to this perimeter, which we do not know. So, as we work through these things, we will get 8x equal to 54. Divide by 8 on both sides. And we will get the reduced fraction of 6 3/4. (54 over 8). All right, let's say we want to do area then. So if I'm going to figure out the area that's missing, and now which one do we need the area of? We need the area of the bigger one. So let's look. Again, use your same scale factor. It's an 8:3 ratio. ABC to XYZ. So I make the same comparison. Do I know the area of ABC? No. Do I know the area of XYZ? Yes. Now, what has to happen though? With area, we have to square. The squared ratio, just like it says right back up here, just follow my formula. This ratio of sides squared equals ratio of the areas. So we're going to hope to avoid that mistake. So that'll give us 64 over 9, the mistake of forgetting this, equals x over 50. All right. 9x is going to be equal to 3,200. When we divide both sides by 9, we get 355 and 5/9 meters squared. That's going to be the area of that other triangle. I don't have to worry about finding the base and the height and the perpendicular stuff. It's all set right there. So these are the notes that'll help you on worksheet 7.5 that is now being assigned.